everyone. I welcome you to this demonstration class. We will demonstrate this membrane filtration unit for the fruit juice. As we know that this membrane filtration nowadays play an important role in the juice processing industry, that is the food processing industry. As whatever the juice are there, so they are treated with the thermal technology. Because of this thermal treatment, some disadvantages are there to the fruit juice, such as there may be a loss of volatile component, there may be loss of nutritional component, there may be loss of color, there may be a cooked flavor, so on. So these are the disadvantages of the thermal treatment. To avoid those disadvantages, this membrane filtration technology can be adopted for an alternative to the thermal treatment. So various type of membrane can be used for the fruit juice processing using this membrane filtration technology. So we'll demonstrate you the detailed component of this membrane filtration unit, the working principle of the membrane filtration unit. Okay. So all practically will show you with the help of this class. So before starting this demonstration program, my research scholar Mr. Abdullah, he will be explaining you in detail about this membrane filtration unit. He will show you the demonstration, he will show you the component, he will show the specification, including washing and other parts of this membrane filtration unit. So over to Abdullah.
Thank you, sir. My name is Abdullah, research scholar under Professor Ramchandra Pradhan, Department of Food Process Engineering, NIT Rourkela. Today, I will be giving a live demonstration video of this membrane filtration system. In this demonstration, I will be explaining you different parts, basic principles and working of this system. I welcome you all to this live demonstration video. The requisites for today's demonstration are a membrane filtration system. What you are seeing here is a membrane filtration system, and the next one is a membrane. What you are seeing here is a 0.2 micrometer microfiltration membrane, which is made up of polysulfone material. And the next requisite is fruit juice. Here we have taken mango juice. You can see this mango juice is turbid and it is unclear. One of the basic application of membrane filtration is clarification. So here we are going to remove the turbidity and haziness of this particular mango juice using membrane filtration system. Another application of membrane filtration system is cold sterilization. Fruit juices contains high amount of microorganisms such as bacteria, yeast and mold. Membrane filtration system can be utilized to remove these microorganisms from the fruit juice. Hence, the next prerequisite for our demonstrations are HNO3 and NaOH. HNO3 and NaOH are the basic chemicals that is required during membrane washing. Membrane washing is a very important step to remove dirt and fouling of the membrane. So now moving on to the detailing of membrane filtration system and membrane. Membrane processing was introduced as an alternative technology to the traditional thermal processing of food. Currently, membrane processing emerged as one among the most significant branches of food processing, with almost 20 to 30 percentage of the total worldwide production of membranes today are utilized for food processing applications and has an annual growth rate of approximately 7.5 percentage. The membrane processing is a non-thermal technique without any involvement of chemical agents and alteration of pH, temperature and phase. Moreover, this technology can work on the continuous process and is more energy efficient and economical. It reduces labor and production cost as compared to other similar conventional technologies such as precipitation, centrifugation, gravity sedimentation, adsorption, solvent extraction, evaporation, flocculation, and coagulation. What you are seeing here is a typical membrane filtration unit. It is divided into two separate sections. This is one section and this is another section. So this section is used for microfiltration and ultrafiltration, and this section is used for nanofiltration and reverse osmosis. That is for fruit juice processing. This portion is used for clarification and this portion is used for concentration. Coming to microfiltration, the microfiltration is a technique involving a large membrane pore size from 0.1 to 10 micrometer, lower operating pressure from 110 to 300 kilopascal, and a molecular weight cutoff higher than 100 kilodalton. Microfiltration membranes is typically made using polymeric materials such as polyamide, chlorinated silica, stainless steel, carbon-carbon composites, and alumina. Like microfiltration, ultrafiltration membranes are usually made using hydrophilic materials such as polyamide, polyether sulfone, polycarbonate, cellulose esters, polyether amide, polyether ether ketone, and polysulfone. As I have already said, the other part of the membrane filtration system is used for nanofiltration and reverse osmosis techniques. The nanofiltration is a comparatively new technique intermediate to ultrafiltration and reverse osmosis. It involves a 0.5 to 2 nanometer pore size membrane with operating pressure of 500 to 1500 kilopascal and a molecular weight cutoff in the range of 200 to 2000 Dalton. Nanofiltration removes components with a small molecular weight, for example, amino acids, sugars, divalent ions, and all microorganisms. However, it allows the passing of certain monovalent ions such as sodium chloride along with water through the membrane. In food industries, nanofiltration is used for demineralization of sugars, the concentration of dyes, milk and juices, and recovery of bioactive compounds from liquid foods. It has higher efficiency, reliability, ease of operation, and lower energy consumption than reverse osmosis process. Coming to reverse osmosis technique, it is also known as hyperfiltration. It consists of a dense membrane with a pore size less than 1 nanometer, an operating pressure of 2000 to 6500 kilopascal, and a molecular weight cutoff of 100 Dalton. It is used for desalination, purification, concentration, and separation. Reverse osmosis is recognized as the most effective method for the elimination of chemical residues, dissolved salts, and inorganic components from water. It can also combine with other filtration techniques such as ultrafiltration and microfiltration. The food industry application of reverse osmosis includes drinking water purification, whey and milk pre-concentration, alcoholic beverage de-alcoholization, and juice concentration. However, higher energy consumption, fouling tendency, and high pressure are some of the disadvantages of reverse osmosis process. As I have already said, this membrane filtration system is divided into two different parts. This is the clarification setup. Different parts of this clarification system includes a holding tank. This is the place where we will hold our feed. See, this is the feed. Currently we have given water as the feed for washing. It also contains two pressure valves, pressure valve 1 and pressure valve 2. It contains a speed controller here. This is a speed controller. Then a peristaltic pump. This is a peristaltic pump. Here it has two pressure gauges to calculate the total pressure, total transmembrane pressure of the process. And it has a membrane holder where we will keep our membrane. This is a microfiltration membrane of size 0.2 micrometer. Its size will be written here. 0.2 micrometer is its size. And the other part of the membrane filtration system, as I have already said, this part is used for concentration of fruit juices. The concentration is an essential unit operation in juice processing aimed to ensure a lesser packing, storage and transportation cost and a longer shelf life. Concentrated juice has less water activity, which makes it resistant and more stable to chemical and microbiological spoilage than the normal juice. Traditionally, juice concentration is carried out using evaporation techniques, which involves high energy consumption and high temperature, resulting in quality depletion due to the formation of off flavor, loss of volatile beneficial components, and degradation of color. However, concentration using membrane filtration is a non-thermal, low-cost technology which doesn't use any chemical agents and phase change. The different parts of the membrane concentration unit includes one pressure control valve, one feed tank where we will keep our feed, then two pressure gauges, pressure gauge 1 and 2, membrane module. Here we will keep our RO or nano filtration membranes. Then a peristaltic pump here, similar to our microfiltration unit. We also have a peristaltic pump in concentration unit also. Coming to the membranes associated with a membrane filtration system, these are different types of membranes. All these membranes were purchased from WaterSup Explorer, Mumbai, India. These membranes have different membrane pore sizes. For example, this is a microfiltration membrane with a pore size of 0.45 micrometer. You can see it is written there, and a surface area of 52 centimeter square. It has a maximum temperature capacity of 40 degrees Celsius, and it can withhold a maximum pressure of 20 psi and at 20 degrees Celsius. Similarly, this is another microfiltration membrane with membrane pore size 0.1 micrometer, and the surface area dimensions, maximum temperature and pressure for this membrane is similar to that of 0.45 micrometer membrane. However, this is an ultrafiltration membrane whose membrane pore size is 50 kilodalton. Its surface area is 52 centimeter square. It can also withstand a maximum temperature up to 40 degrees Celsius and maximum pressure up to 20 psi. Similarly, this is also an ultrafiltration membrane of 30 kilodalton. This is another membrane of 10 kilodalton. This is another membrane of 5 kilodalton. However, this is a reverse osmosis membrane. The basic difference between these two membranes are not only on its membrane pore sizes but also on the membrane module. These two are made up of two different membrane modules. These particular membranes are made using hollow fiber module. The hollow fiber module involves compactly packed bundles of thin tubular fibers. Each bundle is generally made using numerous single hollow fibers, usually in the range of 50 to 3000, thickly sealed on both the ends inside a shell tube. This arrangement makes the hollow fiber modules resistant to higher pressure. The typical hollow fiber diameter is in between 0.2 to 3 mm and has a length in the range of 18 to 120 centimeter. However, the reverse osmosis fibers made using hollow fiber module are exceptional with a diameter as low as 0.04 mm but has a higher resistance to pressure than other fibers. These modules can operate in both inside out and outside inside mode. That is, in inside out mode, the feed flows along the inner side of the membrane fiber and the final products comes out through its outer side. Whereas in outside inside mode, the movement of feed is from the outer area of the membrane fiber and the permeate collects at its inner side. The hollow fiber modules consumes only the minimum energy and have a thick packing density. However, it shows a fouling tendency, hence make it difficult to treat high viscous feeds or feeds with higher solid content. Also, these modules are very hard to maintain and clean. However, this is a spiral wound module membrane. In spiral wound module, two flat sheets of the membrane and a mesh-like spacer, typically 0.03 to 0.1 inch thick, are wrapped together and surrounded in a porous central tube. One edge of the membrane sheet has an opening near the central tube for collecting the permeate, while the remaining three edges are closed together. The liquid feed flows in an axial direction along the membrane surface, whereas the permeate passes through the center in a radial direction and collects outside the central tube. The spiral wound membrane have an average fouling tendency, compact design, more energy efficiency, acceptable packing density, and higher surface area volume ratio. The spiral wound membrane are capable of treating feeds with larger volumes, but necessary pre-treatment should be done for high viscous feeds and feeds with large particulate matter. Other than these two, there are two other major membrane modules such as plate and frame module and tubular module. In tubular module, the modules have a shell and tube configuration where the tube-shaped membrane is fit inside two cold and hot fluid cylindrical chambers. It typically works in a cross flow or tangential mode. In this module, the feed pumps along the membrane center at high velocity, which develops a layer of concentration polarization along the surface of the membrane, promoting to more comfortable cleaning and stable and high flux. The tubes of the membranes generally have a length in between 0.6 to 6 mm and a large inner diameter between 5 to 25 mm, typically fabricated using perforated plastic or fabric support. These modules have a good effective area, low fouling tendency, and are best suited to treat high viscous feeds and feed with high solid content. In plate and frame module, the configuration of plate and frame module is similar to that of spiral wound module. In this module, the spacers and the membranes are arranged together in layers, that is planar configuration, between flat sheets or plates. Hence, it is also known as flat sheet modules. They are more comfortable to maintain and clean but bit costlier. Therefore, it has broader application in laboratory scales. The plate and frame membranes can be used to treat high viscous feeds and feed with high solid content. It generally has a length of about 10 to 60 centimeter and the channel gap is in the range of 0.5 to 10. Coming to the working of the membrane filtration unit, both the clarification unit and concentration unit works on same principle. Today we will be demonstrating how a juice clarification unit works. As I already said, the main parts of a juice clarifying unit is a feed tank. We will be feeding our fruit juice here. Currently we have fed water. This feed will pass through the silicone tube with the help of peristaltic pump. This peristaltic pump will suck the feed from the feed tank and it will pass through the inlet of the membrane at high pressure. Once it passes through the membrane, the juice particles which has lesser size than the membrane pore size will pass through the membrane and it will be collected here as permeate. However, those particles which will not pass through the membrane will be collected through this pipe as retardate. Here the retardate will be recirculated back to the feed tank so that it will again pass through the membrane for further filtration. This is how a membrane filtration unit works. when we switch on the main power plug and when we switch on the peristaltic pump, the membrane start functioning. Here the pump rotates at 121 rpm. We can set the rpm. Here the rpm is set according to trial and error method. I have kept the rpm at 130. Initially the pressure valve will be open. It is open, both the pressure valve will be open. This time the inlet and outer pressure gauge will be 0. Since the pressure is 0, there won't be any filtration. Whatever the juice comes out through the membrane will be recirculated back to the feed pump. That is, there won't be any permeate. However, when you increase the transmembrane pressure, see here I have increased the transmembrane pressure to 20 psi. Both the transmembrane pressure reaches 20 psi. The filtration starts. You can see permeate collecting here, and the retardant is sending back to the feed. Now we will see how a clarification happens in fruit juice. For this purpose, initially we have removed all the water which was present in the feed tank. Now the feed tank is empty and the inlet valve will be closed. Once the inlet valve is closed, the juice should be fed in the feed tank. This is a 500 ml fruit juice which will be fed in the feed tank for clarification. You can see the color of the fruit. It is highly turbid. Once the juice is fed, the peristaltic pump should be turned on, followed by opening of the inlet valve. You can see the juice is passing through the silicone tube with the help of peristaltic pump. The peristaltic pump is rotating in 129 rpm. And since the pressure is 0, all the juice is flowing back to the feed tank through the silicone tube. Now for the clarification, we have to apply transmembrane pressure by closing the pressure valve. I am increasing the pressure to 20 psi. 20 is the maximum psi this particular membrane can withhold at 20 degrees Celsius. Now you can see the juice which is clarified started coming through the outlet of the membrane. This is the permeate of the membrane, and the retardant is flowing back to the feed tank. This is how the clarified juice is flowing out of the membrane. You can see it is a clear colorless fluid. We will keep the silicone tube back so that the permeate or the clarified juice can be collected in this beaker. The major constraint for using a membrane filtration unit is the fouling of the membrane. Fouling is one of the main concern during membrane processing, since it can adversely affect the membrane functioning. In a membrane structure, there are different varieties of fouling, such as biofouling or biological fouling, inorganic fouling, organic fouling, and particulate or colloidal fouling. Biofouling is associated with the formation of biofilm on the membrane surface due to the activity of organisms such as fungi, bacteria, or algae. These biofilms produce biopolymers such as amino acids, proteins, and polysaccharides, which causes fouling. These kind of foulings are also known as microbial fouling. Organic fouling is formed when organic matters are accumulated at the pores. The adsorption or decomposition of magnesium carbonate or calcium salts or other inorganic precipitates on the membrane pores is termed as inorganic fouling or scaling. Colloidal or particulate fouling formation is due to the decomposition of colloids or inert organic compounds on the membrane. Fouling can be reduced or controlled by various methods such as pre-treating the feed with enzymes, centrifugation, ultrasound, and membrane heating and membrane cleaning. Once the microfiltration is over, the clarified juice will be collected like this. You can see it is a very clear, colorless and turbiditless juice. After membrane filtration, the membrane should be cleaned periodically to remove the blocks and pollutions caused by the decomposition of impurities and separation components on the membrane surface. An efficient and periodic cleaning not only reduces membrane fouling but also can extend the life of the membrane. The two most common methods of membrane cleaning are forward flushing and backward flushing. In forward flushing, permeate or feed water is flushed more rapidly into the membrane at high hydraulic pressure. This rapid flow results in high turbulence, and due to this, the impurities deposited in the membrane surface are discharged and released. However, the contaminants that blocked the membrane pores must be removed by forward flushing. In backward flushing, the feed water or permeate is flushed in the direction opposite to the actual flow at high pressure. The flux during backward flushing will be twice as that of the flux during regular filtration. For restoring the flux, and to improve the cleaning efficiency, a chemical cleaning technique or acid alkali wash is usually followed along with backward flushing. Citric, oxalic and hydrochloric acid are the generally used acid solution with a pH in the range of 2 to 3 for the effective removal of the inorganic materials. Similarly, sodium hydroxide solution with a pH range of 10 to 12 is the commonly used alkali solution for chemical washing of membrane. Initially, the procedure that we follows for membrane washing is as follows. Initially, the membrane will be rinsed using tap water at minimum transmembrane pressure and a maximum flow rate for 30 minutes. Subsequently, 0.1% NaOH solution will be heated to 50 degrees Celsius and flushed through the membrane for 30 minutes at the same transmembrane pressure and flow rate. This is the alkali wash that we follow. After alkali wash, again tap water will be used to rinse the membrane until neutral pH. Further, 0.1% HNO3 solution will be heated to 50 degrees Celsius and flushed through the membrane for 30 minutes at the same transmembrane pressure and flow rate. This is the acid wash that we follow. After the acid wash, again tap water will be used to rinse until neutral pH. That is how we wash our membranes after each membrane processing. So now, since the juice clarification is over, we are going to start our membrane washing procedure. For this purpose, already we have prepared chemicals HNO3 for acid wash, NaOH solution for alkali wash and distilled water. First, we will start with water wash. We will take 500 ml of distilled water and we will feed it on the feed tank. This is approximately 500 ml of water. After that, we have to switch on our peristaltic pump. Once it is on, make sure that the inlet valve is open. There should not be any transmembrane pressure during water wash. The water wash will be done for approximately 30 to 45 minutes. The water wash is done, we will remove water from the fuel tank like this. The water will be collected in this conical flask. You can see. Once the water wash is over, we will do alkali wash. For this, we will add 500 ml of NaH solution into the feed tank and switch on the peristaltic pump. Here also make sure that the inlet valve is open and there is no transmembrane pressure. You can see there will not be any filtration happening. The complete alkali solution will be recirculating back as written date. Once the alkali wash is over, we will be collecting the NaOH solution back into this conical flask. Once the alkali wash is over, again we have to do water wash. 500 ml of distilled water should be added into the feed tank and switch on the peristaltic pump. Make sure that the inlet valve is open and there is no transmembrane pressure. Once the water wash is done, again collect the water back into this conical flask. Once the water wash is over, next one is acid wash. For that, 500 ml of HNO3 solution will be added into the feed tank, followed by switching on the peristaltic pump. Acid wash will be conducted at 0 transmembrane pressure. Once the acid wash is completed, we will be collecting the acid back into the conical flask. The acid wash will be followed by a final tap water wash. For this purpose, 500 ml of tap water will be added into the feed tank, followed by opening the valve and reducing the transmembrane pressure to 0. The final tap water wash will also be conducted for minimum 30 minutes to ensure that the pH is back to neutral. This is how membrane washing is conducted.
With this, our demonstration of this membrane filtration unit is completed. I hope you all got an idea about this membrane filtration unit, so that may be helpful to you or for further research. We have already published some of our work at NIT Rourkela. You can also find out those publications. Still, if you have any doubt or any clarification or any suggestion, most welcome, and you can contact me at any point of time for any type of clarification on this membrane filtration unit. Thank you very much.